Okay, this is Mr. Dahlstrom's Pre-AP Physics. We're looking at worksheet number 2, Training Pulleys Continue. This is the worksheet that we got on Monday, 11/23, November 23. Recording this video after school, so if you get the worksheet up there after school, you can realize there. So we're looking at some different problems that we did compared to what we did on the worksheet before that I recorded on Friday, where we had train problems. These are already worked through. And then we had a pulley problem, and then we had a table/pulley problem. So the one we're looking at here isn't necessarily that much more difficult. It's just we haven't had this scenario. We're also going to look on number 2 here. This is not our first pulley, but it's the first time that we have a mass hanging from a mass going around a pulley. And then possibly on the next video, I'll show you just the introduction, and maybe we'll solve this here, the solving of a inclined plane and pulley. And then I'll assign this for you to work on your own. So all of these have no friction, and I plan on making a packet or a set of problems that you'll be working on, and this will be enough of an introduction. Let's go ahead and get started here. So the first thing says find acceleration of system and the tension on each string. The first thing when we see this here is we need to figure out which way this thing is accelerating. And even though the 10 kilogram is the most mass, it's not deciding which way this is pulling because there's no net force on this. So the 4 kilogram being more massive than the 3 is going to cause this whole system to accelerate counterclockwise. So that is a negative acceleration there, which in turn causes this to be a negative acceleration, which also in turn causes this to go up, which is positive acceleration. The next thing that we're going to want to do is draw our boxes, and the boxes here help us isolate each of the masses and make them independent of each other. Okay, there we go. Going a little bit quicker through this because you guys can always pause for the calculations. I already have the calculations here. So let's look at, we have tension 1 that is here, so it's along there, and we have tension 2. So if you look at the 4 kilogram first, in order for this thing not to fall, the string needs to hold it up, so we would have T1 this way, okay? And then downward we would have the force of gravity or the weight, which is M4 times G. That's just 4 times 9.81, which is 39.24 newtons. Okay, that's all we would have there. We're going to ignore the horizontal because there's no friction or no with these problems. For this one, if you have T1 up this way, we have to have T1 because T1 is what's pulling the 10 kilogram mass to the left. But we also have a tension back to the right caused by the weight of the 3 kilogram one, and that is this way. We're ignoring the forces up and down because this is frictionless. We do not have to take that into account. If there was friction, then we'll go over how you might do that. It's not as complicated as you might think. The last thing we're looking at here is the tension, and in order for 3 kilograms to be kept up, it needs to have T2. I'm going to go ahead and cancel that out so I don't overly do that. And then we have the weight of this, which is mass 3 times G, or 3 times 9.81, which is calculated as 29.43 newtons. So there's our free body diagrams of each of these. I'm going to try to separate this out here. We want to write an equation for each of the masses. We might be able to see here that this mass up here is going to have T2 and T1 in the equation. And so how are we going to find that? This mass is going to have T2 there, and then this mass is going to have T1 and plug in there. So it has 3 masses, meaning there's going to be 3 equations. So let's write M equals, or the M4, which we're calling 4 kilograms, and it's good to get in a habit here of writing to the right of that M times whatever the acceleration. So it's M times negative A. I'm just going to write it as that. Any other chances we have to realize that that is negative A will help us in our goal of solving this. So even though it says it there, I want to make sure when I put it in my equation that it is negative. So up minus down, okay? T1 is up, minus everything down, so 39.24, which we calculated as the weight. Okay, that equals M times A, or in this case, M times negative A. So 4 times negative A, or negative 4A. And because we can solve for one of the tensions here, at least algebraically, we're going to go ahead and move the 39.24 to the other side and get 39.24 minus 4A, and we're put parentheses around that because that's a quantity, and that's as far as we can go. Next thing we're going to want to do is write the equation for the 10 kilogram mass, and I'll do it right here. So M10 is 10 kilograms. And because this is moving down, it's pulling this to the left, so this would also require a negative acceleration. I'm running out of pencil ink here. Get my pencil. Okay. And, okay. The equation we would have is right minus left. Right is T2, so T2 minus T1, T2 minus T2, right minus left, equals 10 times negative A, or negative 10A. And at this point, it doesn't really benefit us anything to really rearrange the equation. Here, there was only one tension, so we could do that. But here, we'll just leave it like that. And then we'll look over at the mass 3. Give myself some room for the 10 mass here. M3 is 3 kilograms. Make sure we're careful here. The 3 kilogram one is now going up, so it would be M times positive A. Up minus down. Up is T2 minus the force of gravity, or the weight, which we calculated as 29.43, 3 times 9.81, equals 3 times positive A, or just 3A. And once again, we have a scenario where we can solve for one of the tensions in terms of the other values, and so we'll add 29.43. T2 equals 29.43 plus 3A. Go ahead and put parentheses there, parentheses there. The reason why we're putting those parentheses is that we are now substituting this quantity in there. And you can see, especially for T1, we're going to be substituting into there, and we don't want to miss that the negative has to be distributed throughout that. But don't try to plug and distribute, just write it as is. So T2 over here, so that's 29, I'll give myself some space here, 29.43 plus 3A minus quantity, 39.24 minus 4A. Okay, that's that, equals negative 10A. Here we want to make sure that we distribute that negative here. So that negative here, that positive makes that negative, makes that positive. Hey, I'm going to move my 10 over here to get all the A's. So 3 plus 4 plus 10 is 17A. And I'm going to move 39.24 over, and I'm going to subtract 29.43. So 39.24 minus 29.43. 17A equals 9.81. That's not a coincidence. We'll talk about that in a little bit, why that is. And we get here acceleration is, we're going to go ahead and round up 3 decimal places, because we've seen if we round too much, these tensions can be not as precise as they normally would be. So there's acceleration. The fact that that is not negative right there means that we correctly predicted which way this system was going to go. That was going to go down, that was going left, and that was going up. So now what we can do is we can plug acceleration, basically we use this, we plug this acceleration into there, plug that also into there, and I'll go ahead and just, for sake of time, this one, when we do that, we get 36.93 newtons. And for T2, we get 31.16 newtons. Now, we can look at this conceptually before we end this problem. We talked about with trains that the front of the train, the force in the front of the train has to pull all the other masses here. So you can consider this force right here, the weight right here, the front of the train. This has to be the most force, followed by this force. So this has to hold up all of these. This only has to basically accelerate these. This has to accelerate this. So this one in the front is the most, 39.24. Tension 1 should be the second most, and it is 36.93. T2 should be the third most, and it is 31.16. And then the last one is 29.43. So this is the force to accelerate all these. This is the force to accelerate this. This is the force to accelerate that. And that is the force if the acceleration is 0. That's just the weight of it. Okay. I'm going to go ahead and pause this and we'll make little mini videos there. So that's one if you have a table problem, and we're going to go ahead and move on to the next one. So I'll call the video here. Okay, see you on the next one.